talk about density and mass function, so called PDF and PMF, probability density function and probability mass function. And we will be seeing a little bit about the relation of PDF and PMF with the CDF, the cumulative distribution function that we just covered. So let us start. Associated with a random variable x and its CDF f of x, fx. We talked about it. If we have a random variable x, you can always have a CDF of it is another function. It's saying associated with this function and this function, another function, either called probability mass function or probability mass function in discrete case and probability density function in the continuous case. So there is another variable associated, another function associated. Another means one is CDF and another is PDF or PMF depending on the type of variable. If variable discrete, then we say PMF. Um, if variable is continuous, then we say PDF. Both PMFs and PDF describe the how probability is distributed. All right, let us just move ahead and see the definition of probability mass function. So probability mass function of a discrete random variable x is fx of x is defined as uh, this and this. This is the definition. Probability x equals to x for all x. And it's like for all x belongs to real numbers. Alright, so now let us do an example that geometric PDF, geometric probability for a geometric distribution of 1.5.4 that we just did in the second last lecture from now. Then px of px equals to the x is equal to the 1 minus px minus 1p when x is equal 1 to 3 and so on and 0 otherwise. Recall that probability of x equals to the small x equivalently fx of x is the size of the jump of the CDF at x in the discrete case. Hence, for positive integers a and b, a less or equal to the b, probability a less or equal to the x, x less or equal to the b, we can do what? So this is like probability a less or equal to the x, x less or equal to the b is what? So for any integers a and b, so it's kind of like we are collecting probabilities from a to b. That means we will be summing up the PDF. Why are we summing up the PDF while calculating this? It is saying like probability x equals to the a is the jump of, let's say if I talk about x equals to the a, then probability x equals to the a is what? Fx of a and so on. So if I calculate a, like if I have like a, then a plus 1, a plus 2 and let's say b. So for finding probability a less or equal to the x less or equal to the b, this is x equals to the a, probability of x equals to the a, x equal a plus 1, x equal a plus 2 and so on. And probability x equals to the a is actually fx of a. So that's why we are writing the probability mass function while calculating the probability of an interval. So this is this, and when you put this, then you have a special case like it's saying x less or equal to the b, then this k equals to the 1 to b and this fx of b. All right. So now standard convention is to use uppercase for the CDF and lowercase for the PMF or PDF. For a continuous random variable, uh, point probabilities are zero. So it's saying now that if x is continuous, then probability of x equals to the x is zero for all x in R. So it's not hard to prove this, but we need to like show how. So one thing we observe that probability, sorry, that x equals to the x is subset of x minus epsilon less than x less than or equal to the x. That's true because we have x equals to the x, and this is between x and x minus epsilon and x, because x minus epsilon and x contains x. So this is x equal to the x is contained here. So when you do probability of x equals to the x, this is this, and we already showed this. Then if you take x epsilon approaches 0 to 0, it's like epsilon approaches 0 from right. Um, then we have what? Since this is right continuous, so this will be what? Fx of x. So this cancels with this. Hence probability of x equals to the x is 0. In the discrete case, the CDF is obtained by the summing the PMF. In continuous case, so how do we like obtain a CDF? By summing the PMF. Like it meanings is that fx of x equals to the probability of x less or equal to the x. So if it's a discrete, then we are summing overall x. CDF is obtained by summing the PMF. So what? When you sum the PMF, then you get a PDF. So like in the previous case, we saw that here, if you sum the PDFs, you get what? CDF. So similarly, we should have that in continuous case, the analogous operation is the integration. That if x of x must be minus infinity to x fx of t dt. Now question is here, is this a definition? This is for sure a definition. All right. Now question is this a definition or this is just an equality? Hmm? What do you say? Is this the definition or equality? Is this like I'm an equation or identity? For sure, this is identity, but okay, that's true for all lights. So summing, yeah, this is actually the definition of continuous random variable. So this is actually definition. Um, no. This is definition of continuous random variable because probability x belongs to A is A fx of t dt for all a belongs to Borel Borel cells. Okay. So if you take now x less or equal to the x, then you get like minus infinity to x and so on. So it's saying we get fx of x equals to the minus infinity to x. So we are getting CDF by summing all of the x's t's from minus infinity to x. If this is the case, then we say this is a PDF. If fx is continuous, then by fundamental theorem of calculus, so I think this is not definition, this is equality. I mean, in the sense of equation. So, if fx is continuous, then by fundamental theorem of calculus, if you take if x is continuous, like if this is continuous, which is not necessarily for like the for a continuous random variable to have the PDF continuous. We are saying if this function is continuous, then you can apply what fundamental theorem of calculus, that derivative of fx of x equals to the fx of x. Probability density function or fx, probability density function or PDF fx of x of a continuous random variable. Um, x is function satisfying fx of x equals to, so what? So it's the definition of what? It's the definition of continuous random variable. If function is continuous, it must satisfy this thing. That and this thing is what? Probability of x less or equal to the x. The probability density PM of a continuous random variable x is a function satisfying this. So let us confirm from AI that what is actually a definition here. So now it's saying this is a definition of PDF. Oh, this is not definition of continuous random variable. Continuous random variable definition is that if x is continuous, then its cumulative distribution function is continuous. Yes, x is discrete if its cumulative distribution function is stepwise. So here the the definition of PDF is that if you sum all of the such a function that if you sum up to minus infinity to x, then it should give you fx of x. Then we call it a such a function is called PDF. And is this unique? For sure, it should be unique. For sure, if this function is non-negative. So we don't know at this point it's this is non-negative or not, but it must be non-negative. Let us see. Let us see. We will see why it's non-negative. So this is definition of um. So this is satisfying. Again, this is not a definition equality. So this equality is what actually this is just a satisfying equality. So this is like satisfying equality. Like if this happens, then we will say this such a function is called PDF. A note on the notation. The statement X has a CDF fx and is often denoted by X is a CDF fx. And similarly, we have notation for this PDF. And if X and Y have the same distribution, then we say X is related to Y. Like X and Y is same distribution, not related. Since probability of X equals to the X is equals to 0 for a continuous random variable, now then probability A less than X less than B up to so on. These if you include a point probability or not, it does not matter. So this is very much clear. And now it's saying why we have that probability of A less or equal to the X less or equal to the B. Why it is the case that this is A to B? DDT. If I take the left hand side, now if I take A equal or not, it does not matter from here. Alright. So this is what this is actually fx of B minus fx of A. And this is what minus infinity to x. If this is a PDF, alright. If this is a PDF, then this is what fx of t dt minus infinity to x fx of t dt. Minus infinity to, sorry, not x, minus infinity to b, and this is minus infinity to a. So this is a is less than b from here. So this must be then a to b from calculus. So that's why you have this, and this is directly from here. But the question was like why this is happening here. So this comes from like from these steps. This is for a continuous random variable. If function is continuous. And having PDF fx of x. Now for a logistic distribution, we have fx of x is this. Like this is CDF, and we find PDF by this, and we note that this is continuous. After taking derivative, we came to know this is continuous. So hence taking a derivative of this gives you the this one. The area under the curve. Yeah, this is we just showed in the previous steps. So this is true because you can give equality here, and this comes from here, and this is just from calculus. So area under the fx of x gives interval probabilities. So area under the PDF gives you the interval probabilities. That is really, really, really true. A function fx of x is a PDF or PMF of a random variable x. If and only if, what happens? Fx of x is non-negative for all x, and summation this is 1 and this is 1. So what? This is if and only if, right? So one thing that yeah, this is if and only if. Now if I talk about discrete case, let fx be PDF. We know that fx of x is equal to the probability of x equals to the x, and this is non-negative for all x in R. So this first thing is satisfied. Let us try to find this. So summation fx of x over all x equals to the summation probability x equals to the x over all x, and if you sum all of them, then you get probability of the what? Sample space S, and this is 1. This is one thing. Like the first direction is clear, like this one is also clear. Let us talk about um like we are done with this first direction, and now take the continuous case. We know that a function is PDF if it satisfies this sign. Dx. Now question is why this function is non-negative? Why this function is non-negative? Let us see from here. For a PMF, this is this, this is this, this is this, because these are disjoint and their union is the whole sample space. This is very much clear. If fx is PDF, then by definition, this happens. That's true. That's true. That's really much true. That's really much true. We seeing that if x is non-negative or not? Yeah. Since yeah, we wanted to show that f x of x is non-negative. So how do we show if x of x is non-negative? Since fx is non-decreasing function, then for h to be positive, 0 is less or equal to the x. So that's very much true that fx of x plus h minus fx of x is non-negative, because this number is bigger than this number, because x plus h is greater than x and the function is increasing. So this is non-negative. And this is x to x plus h and fx of x, fx of t and dt. So now from x to x plus h, from x to x plus h, so it's saying like from here, it implies that this is overall non-negative. It implies that fx of x must be non-negative. Why, bro? This should not be the case. This is not a good proof. I don't like it. It's saying whenever fx is continuous. More generally, non-negativity is part of defining property of a density function. I don't get it, bro. I don't get it. Non-negative is comes from the definition. Why? Why non-negativity comes from definition? Let us ask AI. We want to show that is greater or equal to the zero when is PDF. Show me that. I feel the proof given here is wrong. Your concern is valid. The displayed argument is incomplete as written. From this non-negativity, we cannot immediately say fx of x is non-negative. So what? A function could be negative at this point while its integration over every interval remains non-negative. The missing step uses the assumption that fx is continuous. Why do we need to assume this fx is continuous? X is continuous, I know that. Why x fx is continuous? Since fx is a CDF and it is non-decreasing, therefore for every h positive, using this we get this. Ah, I see. He is dividing by h on both sides and making it the CDF, fx of x, derivative of CDF. And if fx of x is continuous, then its limit must be non-negative. Yeah, 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 yeah. I see. I see. I see. I see. I can clearly see that. But we need to assume that fx is continuous. If so, what was the question here? If x is continuous, then um, is it necessary that but then why the previous proof assumes fx is inverse. At every specific point, non-negative. From this, we can conclude without continuity, only that fx is non-negative almost everywhere. That means fx may be negative at isolated points or at some set of probability of length 0 without changing any probabilities. Continuity prevents this. Non-decreasing. Therefore, textbook is saying that if density is continuous, its non-negativity follows pointwise from the CDF. Yeah. So we don't need to actually prove this thing. This is non-negativity comes from part of definition. All right. So. Next, showing minus infinity to infinity is 1 because we can say minus infinity to infinity, fx of x is equal to the limit x approaches infinity minus infinity to x, fx of x dx. And this is equal to the what? Limit x approaches infinity, fx of x. And this is 1. Alright. So what? We are done. So we are done with the forward direction. If we have the reverse direction, then what? For example, if x is non-negative and the summation is this, then why we have the inverse is true. First consider the discrete case. Suppose fx of x is non-negative for all x and this happens. Define this to be this. Then why this is non-negative? Yeah, this is already assumed. This is non-negative. No. Yeah, this is already assumed to be non-negative. We wanted to show what? That this is PDF and it's already a PDF. And total probability is 1. So this gives a legitimate PMF. That's it. This directly comes from like trivial statement. So now considering continuous case, if x is non-negative and this is 1, then what? Then we define if x of x to be minus infinity to x, fx of t dt. If we show that this satisfy all three axioms, that limit x approaches minus infinity is 0 and limit x approaches positive infinity, fx of x equals to the 1. This is first thing. And fx is non-decreasing. And third thing, fx is right continuous. If we show, then we are done. So we define this. We show non-negativity. We also see 0 part. We also see 1 part. Finally, fx is continuous. Oh. So minus infinity to x, fx of t dt. This is fx of x. And it's saying like it's continuous by definition. Integral is continuous, I guess, from this thing. This is continuous, so hence right continuous. It's saying any non-negative function can be um, PDF.